Yes. Okay. So there's some black spot on the slide, by the way. So in 1926, almost 100 years ago, the vision Nikola Tesla stated, when a wireless is perfectly applied, the whole Earth will be converted into a huge brain. This summarizes what we are trying to achieve with 6G. In my group, we've been working on 3 projects that actually are going in this direction. One of the projects is 6G Arrow. The project has been presented just before, and in which we have this collaboration between Europe and Korea, in which we have 11 partners, and 13 partners for 4 European countries and from Korea. And mainly we are dealing with AI native systems, and one of the technology pillars is semantic communication. Then we have another, I have another project which I'll personally coordinate again, which actually it's on goal-oriented at semantic communications. This is refocusing that is working on the fundamentals there. We have 11 consortium partners plus 1 partner from Singapore, STUD. And one of the achievements we have done now after 1.5 years of work is actually defining a framework for having architectures enabling semantic communication. This is an example we've done, for example, in the case of ORAN, so with the introduction of semantic RIC elements and so on. Then a third project that I'm coordinating as well, which actually goes in the direction of semantic communication, is the 6G DISAC, which actually it's a distributed integrated communication and sensing, in which one of the pillars is about semantic communications, and actually in order to define new waveforms, also define new fusion methods with semantic communications. So what we have been doing so far is actually up to 5G, building generation of content-blind transmit without understanding approach. We have not actually intelligent agents in the system, right? And actually we have followed the mantra. Of Shannon. We're following the idea that in order to have more capacity, which was the target, either we are improving the bandwidth of the communication and or we are improving the number of uncorrelated signal paths, means actually number of antennas, the number of network elements, so densifying the network, either introducing some smart relays like we come from intelligence interfaces. And then the third path was actually, and is actually still, the improvement of spatial efficiency of the system by, for example, having better beamforming algorithms, having better antenna dBi gains, the communication, new waveforms, new modulation, and so on. So this was the race until today, because actually we have been looking for reproducing exactly what we had at the submission, right? Now the idea is different, because we have, as also was said before by a previous speaker, we have the possibility to exploit intelligence at the transmitter receiver so that we can just suggest what we're gonna transmit. So there are a first secret I want to share with you is that we have at least 3 big paradigm shifts in 6G. First one is that we can go for what we call goal-oriented communications. We heard also about that in the case of agentic AI from a speaker from this morning. We go from transmitting the content-blind data to have transmission which is goal-oriented, so actually just the data with the right precision, with the just right amount in order to achieve a task. Then the other one is that we can shape the communication medium in order to accommodate a better environment for communication. In order that is just actually, it's a change according to what we had before, where we consider the communication channel is dictated by nature. And third one, so the one which I'm more fan of, is the native semantic communication, where we move from content-blind communication to understand first, then share only what can be deduced or inferred by the intelligent receiver. So semantic communication brings benefits, but also brings challenges. So benefits, for example, is the use of resources in the energy efficiency, latency reduction, better spectrum use, but also in terms of improving the scalability, also integrated by natively integrated in the AI and machine learning, having also cross-domain efficiency, interoperability, and so on. But actually, there are a lot of challenges. For example, first challenge is actually today, we don't have a semantic information theory established. So we can work on AI modules, but we cannot really have bounds of performance. We don't know if we are reaching the limits of that. So there's a lot of work ongoing there, but probably because AI is advanced that fast, it will arrive after we already produce most of the solutions. The other thing is that different devices might interpret semantic in a different way. So also we call the knowledge, the logic representation mismatch. There's a lot of new complex trade-off, things about the concept of time, how it changed with AI. And also have problems about transition, still open. And also the need to be backward compatible, either to enable coexistence between semantic and not semantic user in the system. So I will not go too much into this detail, but then we have to change also the metric with which we evaluate the system. And I suggest if you are interested to read this deliverable to the 2OCG Goals project, we list more than 24 different metrics. What is the game changer here? Because you don't need to have identical reproduction in the receiver, you want to have something which is similar, something which is equivalent of what you have to do with. An example before, in the presentation before, we did this cat, right? You don't have exactly the same cat, you don't have exactly the same environment, but if it's sufficient to what you have to do. So this set of metrics are made in this direction. And then we have a lot of gains. Here I'll just show you some kind of gains we have with our experimentation. We can gain in terms of compression in the case of text communication, which is not the most favorable one for showing high compression. We have about a factor of 200. In case of video, we can also achieve something around 1000. We can also have a speed up about AI training. That's very important. So the communication is also a way to train while communicating. And this example, we have two robots that have to coordinate to work together, and they don't use the same logic at the beginning, and actually they're trained to work together, they converge in a common model. And actually here is an example of factor 20 plus or gain. And then other thing, let's consider you have network elements. For example, antenna and massimo elements in RS. Actually, we can really use much less elements in the communication. And because we can accept more noise, somehow we can be less performing in a way we set the physical level. And this is an example where we show that we have a factor of 6, for example, reduction of elements we need in antennas. So another thing that most of people understand is the robustness. I guess all of you read this text. If you think this text is full of errors, there's a lot of noise. So the message here, you can pretend not to have a perfect communication, but still be understood. And this is because at the receiver, you have this reasonable capability. But at the same time, okay, the slides are not going in the direction I like. At the same time, if I give you this text, maybe it's not that easy for you to read. Maybe you have to read twice or 3 times. So actually, that semantic robustness depends also on the transmitter and receiver alignment, how both speak the same language, they use the same logic. So there's this convergent phase that most of the time we forget in the semantic communication, but it's very important. So the secret number 2, indeed, is that to use semantic communication, we need this, what we call semantic plane. That means actually we need a logical layer in which we convey all the important information and interfaces to have semantic related models to interact. And there's a set of advantages here. Mostly, I would say we can enable joint adaptation and reasoning between AI models. And so we can transform the network from a blind bit pipe transmission to intelligent agents coordination. We can also have new type of cross-layer optimization in which actually the intelligence comes into the play of the optimization. And we can also have more resilient efficiency, because actually errors that are present on the bits not always matter from the point of view of understanding. It was an example of the text I showed you before. The secret number 3 is actually that exists an invisible semantic logic channel, which carry concept, intent, and task relevant. Let's say I tell you, let's meet in the weekend. I was making an example before lunch. And actually, if you come from a European country, you understand Saturday and Sunday. But if you come from an Arabic country, you understand Friday and Saturday. So either if your physical level communication deliver exactly weekend as a message, you completely get it wrong. So this is the present is logical channel, which is very important. So this is an example. For example, you don't have the video here. So this guy is selling a vase, say 1,000,001, 1,000,002, 1,000,003, and in a Germanic-like language, you would say, actually, he broke the vase. So what you put attention on are who did that, not what happened. So your attention mechanism, your transformers that you're using in AI, indeed, will focus more on who, more than the reason what happened. On the contrary, in Romance-like language, you would say the vase was broken. So remember the intention, not who did it. So just to give you a point, that actually the logic is very important and conditioning the way you perform the semantic communication. So the secret number 4, you need a feedback channel that goes beyond bits. In traditional communication, what you have is that you have CRC, knowledge, negative acknowledgement, so you have error, not error. Here, there's much more degrees of information we can share. We can share information about the ambiguity, the misunderstanding, the context. If what you receive indeed helps, you understood what helps to achieve another goal, and so on. So all this information require new study. This is an open topic of research. Then at secret number 5, I would say the ambiguity is not noise, so you don't have to fight against ambiguity, but actually it's a catalyst. Because actually, by having ambiguity, you can learn how to handle ambiguity. You can train the system. Then, borrowing from Voltaire, this sentence which I like a lot, common sense is not a common. This is also true in AI. So you have to align if you have no common sense. You can have no common sense because you have different training, because you have different background knowledge, you have different neural network models, you have different task or goal. You have also different way to quantize, to represent the information. The other secret is that because we are, most of us working on really on the telecommunication business and not only on the data science, we can also exploit somehow the physical signal, so where waveform signal can whisper semantics, not only transfer symbols. And by doing that, you can somehow have a joint optimization of the waveform and the needs of the semantic interpreter, so that you can have also control degradation. You can somehow tolerate noise, as the example of the text before, and degrade the waveform in order to have more compressed communication, overlap two signals on the same waveforms, and so on. So all these things we have been doing that we're very interested in that. And then also the last secret I want to share is that it is very hard to standardize at the moment this kind of protocols, because actually they have, classical protocols in this are kind of, I would say, deterministic in the way we do encoding and decoding. Here with the semantic system, we rely on learn, encoder, and decoder, which evolve with data, which evolve with time. So actually the capability of a transmitter and the receiver to extract, interpret knowledge, extract, interpret semantics, evolve over being exposed over time at different other users. There is the good news that either there's not yet a consensus on how to implement in 6G the semantic plane or planes related to semantic or slices related to semantics. Actually, there are some standardization groups that are already work on some related topics. For example, the ETRI SIG SAI. We are working on semantic aware AI network communication. The TPP SA1 and SA2. We actually work on concept. We are indirectly, by working on intent-based networking, indirectly linked to the semantic communication. And there's also an IITU some work which is purely goal-oriented semantic communication level. So by the moment of discussion, we hope that this body will be mature enough to grab some information for us. So by using the semantic communication, indeed, the message is also that we can change the way we approach the CG pillars. For example, we have been speaking a lot about the difficulty to go higher frequency. Like we have blocking with millimeter wave spectrum. We can have higher nightmares using subterrestrial communications. For example, we have a lot of distortion at the power amplifiers. But in semantic communication, we can introduce this kind of robustness to noise and errors in order to relax some of the constraint. For example, for the PA, we have some kind of semantic pre-distortion methods for which we are much less sensitive to this distortion introduced at these kind of frequencies. In the ISAC context, we actually can, for example, perform specific semantic fusion in order, for example, to harmonize and actually use heterogeneous sources for the same task achievement. And you can understand easily that actually this is because by passing through an abstraction level, which is a semantic, if it comes from text, if it comes from video, if it comes from sound, if it comes from an image, once you are at the abstraction level, is not an issue, and then you can fuse in a better way. Also, speaking about intelligent antennas, which most of the time requires huge number of elements, it requires very strict coordination. Here, in this case, you can relax all this, thanks to the semantic communication, but again, you can be suboptimal in a control way. And also things very specific to the semantic and generative AI. So I'd like to wrap up the discussion with an example that I give sometimes that I really like. Semantic communication, so started from what was somehow the Shannon approach, one was proposed from Shannon, and going to what actually was proposed in the vision of semantic communication from Wither, actually collaborated from Shannon. We can say it's like if you having a first meeting, a date, and actually where you introduce each other in a very polite way, where you can kindly ask and probably ask with a scribe request what you want to have, and then you thank each other after receiving what you want, what you ask. Then after several months, you know each other, and you have a brief introduction. You don't need so many details. So you ask with the described request, and you have a brief thanks. Then after several years, what you have no introduction anymore. You expect the other to do the action, and you ask with a very short request, and there's no thanks. And after a whole life, actually you're just able to hear each other, ask with a quick eyes contact, there's no thank, you just wait for the next contact. So by training while communicating, you can reduce all this redundancy in the communication. You can really go to the need part. And this is actually one of the things we really try to do with semantic communication. So I'd like to thank you for your attention. If you want some more information, I show you here a number of reading. You can have this nice Nature Review paper, which a couple of pages really give you an overview of what we do. And in any case, you can ask me now or later any questions, and I will be very happy to answer. Thank you for your attention.